Welcome to the PowerPoint to review sound, waves, and vibrations. Remember, it's chapter 25 and 26. Quiz on, what's today's date?
20th.
Today's 20th, so 21st is tomorrow.
Yeah.
And then the test is on Friday. Be prepared. Make sure you try to predict what each slide is going to be. If there are any calculations to do, have a pad and paper and calculator ready to get started. All right, the first thing we're going to want to do is we're going to look at vibrations. These are sound vibrations. You can see that there are waves that are there are concentric rings that are close together and those that are far apart. The ones that are close together are called compressions, and the ones that are farther apart are called rarefactions. These are called longitudinal mechanical waves. They can be converted to transverse waves, where the peaks, the crests, are the compressions, and the trough are the rarefactions. Here are two transverse waves, same frequency, identical frequency, but wave B is a greater amplitude. Okay, now here is a slide which shows you the conversion of a mechanical longitudinal wave and a transverse wave, where the rarefactions are the troughs and the compressions are the crests. The distance between the compressions is going to be a wavelength. The amplitude, now look at the amplitude, it's actually half the distance between the crest and the trough. Here's another example where I am converting sound, the mechanical sound waves, to transverse waves. Notice again, the amplitude is actually half the distance between the trough and the crest. You see that? There's the axis, and the axis is called the rest position or nodal axis. That's where the nodes are, and that's obvious in this part. It says the incident and reflected waves interfere to produce a standing waves. The nodes are places that remain stationary. You see the girl with the rope is going, is the top wave is the incident wave, and that's going forward to the wall and then coming back again. When the waves cancel out because they're out of phase, they cancel and you get no wave. Here's something. And this is when you think of a wave, you think of the ocean. And here's a picture of one of my students on summer break, sitting on a post in the middle of the ocean, kind of hanging out. And they're dressed like a bird. It's pretty good makeup job. And the distance between the waves is 1 meter, and the velocity is just 1 meter per second. So they're two separate quantities. Now, waves can be not only sound, but they can also be light. Here it says electrons in the transmitting antenna of a radio station at 960 kilohertz. Now, a hertz is a frequency per second on the AM. So if it's 96 kilohertz, it's 96,000 times each second you have a vibration. Now here's another slide on standing waves. You can produce a variety of standing waves. Shake the rope until you set up a standing wave of 1/2 wavelength that's just up and down, and then if you give it a little bit of a shake, you can produce one wavelength, and you give it more of a shake, you can produce 1.5 wavelengths, and the more energy you put in, the more wavelengths you're going to be, and the greater the frequency. Shorter the wavelength, greater the frequency, higher the energy. That's going to be very important for chapter 27. Okay, here are some things about the mechanics of waves. You have crests, you have the trough, you have the amplitude, you have wavelength, you have phase. If you have phase, you would have out of phase. So the beginning of the test tomorrow will be basically on the mechanics or the structure of waves. Now, chapter 25 is on waves, waves and vibrations. Chapter 26 is on sound, and chapter 27 is on light. So chapter 25 is actually meant to do sound and light. It's basically an introduction to waves. And here I have another wavelength. It's really one cycle, okay, one cycle. And that pendulum's going up and down, okay, and that's the amplitude is half of that. Here's another example of the conversion between a transverse and a mechanical longitudinal wave. Here they're saying that the compression is the trough. It doesn't really matter as long as if you put one trough as a compression, all troughs have to be in compression. So it doesn't matter if you flip it. It doesn't really matter as long as the conversion, you have the troughs relative to the compressions, and then the peaks would be the rarefactions. Now we're going to start talking about resonance, and the resonance is the girl is pumping her legs in rhythm with the swing, producing a greater amplitude or greater resonance. All right, we're going to stop for a second. We will talk about this particular slide when we do resonance, but I put the slide here to just simply show you that a wave is simply a cycle. You have one cycle from peak to peak, and that's what this girl is demonstrating. From high above down to high above in the back to high above in the front. It's one cycle, and it keeps going back and forth as a wave does. It's a cyclical event. Now, when you drop a pebble or anything in water, you get these concentric rings going out. You've all seen it. Okay, so let's start our analysis of the Doppler effect by understanding the nature of concentric circles as a result of a disturbance in the center of those circles, such as a drop of water and then the production of waves as a result of that. Now, the picture on the left is a bug that's flapping his wings, whatever the case may be, and producing these concentric rings. Now, if the bug moves to the right, look what happens. The waves are compressed between the bug and point B, and between the bug and point A, the waves are what? Are wider apart, creating if you want, a lower frequency as opposed to the higher frequency. So here's a better example of the Doppler effect. You have the observer A and B, and they're both stationary. If you're in front of the noise or the noise is coming towards you, it's going to be a high frequency. Okay, lines are close together, and if you're the observer B, you're going to hear a lower frequency, as is indicated here. Now, the next picture shows that. The top one shows that the pitch of sound is higher when the source moves towards you and lower when the source moves away. So the listener is going to hear the fire engine coming towards him, but then when it passes by, he'll still hear it, but it will be at a lower frequency. An application of this is a police radar. They have waves, short and long waves. Now remember, we're talking about the top one is sound and the bottom one is light. Okay, this is called the Doppler effect. Can also be talked about when it comes to stars at various distances. So let's read this together, and very important. The next few slides are going to be red slides. So read along with me. The Doppler effect also occurs for light. When a light source approaches, there is an increase in its measured frequency, and when it recedes, there is a decrease in its frequency. An increase in frequency is called a blue shift, increase in frequency. Greater frequency, higher energy, blue. Lower energy, red. Because the increase is towards the high frequency or blue end of the color spectrum. A decrease in frequency is called a red shift, referring to the low frequency or red end of the color spectrum. Different distant galaxies, for example, show a redshift in the light they emit. A measurement of this shift enables astronomers to calculate their speeds of recession. A rapidly spinning star shows a red shift on the side turning away from us and a blue shift on the side turning towards us. This enables a calculation of the star's spin rate. Please go over this slide again and put it on pause. Very important slide. Seismologists, we saw a movie Core. When an earthquake occurs, the energy release, the sudden release of energy produces waves. Seismologists study and interpret those waves in order to determine the strength and location of the earthquake. They compare the speed, amplitude, and reception of primary longitudinal waves with secondary transverse waves. Because they understand how waves travel and the material through which they pass, seismologists are able to describe earthquakes, learn about the composition of the earth, and possibly predict future earthquakes. Seismologists conduct research from university and government facilities such as the National Earthquake Information Service, otherwise known as NEIS. When you are exploring for oil or anything of that nature, there's a fundamental architecture that you're looking for when you're looking for oil. So you put explosives in the hole, you set off the explosives, it makes a big bang, and you study the sound reflection. And this kind of quote-unquote sonar activity where you're studying the reflected sound waves will describe a fundamental architecture. And if it's the fundamental architecture of oil, then you would drill a hole. Now we're going to talk a little bit about the speed of sound. The speed of sound is the product of the frequency, and it is the product of the frequency and of the wavelength. So you have a bell ringing, you see that the wavelengths are such, and you simply multiply that wavelength by the frequency, and that will give you the speed of sound. If you look at the ratio, the object speed divided by the speed of sound, that gives you the Mach number. In other words, is it Mach 1, Mach 2, Mach 5, transonic, supersonic, hypersonic? Now, when you're talking about these kinds of numbers, you're talking about breaking the sound barrier, the supersonic, the greater than 1 Mach. And you get this telltale conic shape of the pressure wave that is released when the plane goes through what has been known as the sound barrier, or when the plane exceeds the speed of sound, or when the plane exceeds Mach 1. Now, Mach 1, the plane is going faster than the speed of sound. Now, the next you have less than the speed of sound. You have 4 pictures, A, B, C, D. Okay, you have the left one is the speed of sound, the less than the speed of sound, then the speed of sound, then greater than the speed of sound, and then much greater than the speed of sound. This conical shape. As long as the object is beyond the rings of sound, then it's going greater than the speed of sound, or some ratio, some Mach number. This also emphasizes this, where you have the movement. In this particular case, you have movement from right to left. You have the stationary, you have moving slower than the speed of sound, moving at the speed of sound, and then moving faster than the speed of sound. The next picture is a little confusing. The plane doesn't look like it's built to break the sound barrier. It looks more like an old style crop duster. But anyway, I don't know if it's a made-up picture or not. But the point is that this cone is similar to the cones in the last picture that were going the speed of sound. And the picture, the next picture, where you have this kind of like you have this obtuse angle, this angle that is formed when you break the speed of sound. and listener A has heard the shock, B is hearing the shock, and C hasn't heard the shock yet. This I don't know what else to say. This angle, the structure that's created by these concentric rings that are no longer concentric, actually, will indicate that the plane is going to have this thunderous clap, this breaking the sound barrier. This is the beginning of chapter 26, the chapter on sound. The next several slides are going to be on ultrasound. Ultrasound is a very, very high frequency sound, usually between 2 and 18 megahertz. That's between 2 times 10 to the 6th and 18 times 10 to the 6th hertz. This is an example of what happens when a woman undergoes an ultrasound to see their baby. And it's actually extremely simple, and that is that sound waves are reflected off the baby and reflected back, and the image is caught on a computer and described. So many people have this done for a variety of reasons, and you can also see if there's a problem. It's oftentimes a diagnostic tool that can determine whether or not medical problems are going to occur in the child. Now, this is also something that's used for medical procedures in a variety of different areas. Just think about it. Anything in the human body that has to be viewed would use this ultrasound technique, just like a bat uses sound, like a sonar, to detect distances and how to fly. Instead of eyes, they will use sound. So the same thing is true in medicine. If you have an echocardiogram, that means that the heart is looked at for various abnormalities. You can have your kidneys looked at to see maybe you have a kidney stone, maybe the structure of the kidney stone is not what it should be. People have colonoscopies. Instead of the invasive form of the colonoscopy, these are pictures here of 3D ultrasound colonoscopies, where the computer actually puts together a 3D to see whether or not there are polyps which may need to be removed from the walls of the colon. So these are 3 separate shots in various parts of a person's colon. This takes getting used to. Here is an abdomen, a shot of the abdomen to see whether or not there might be something wrong with the person's abdomen. So many times ultrasound is used in a variety of different has many different medical applications. Here it says ultrasound is used in medicine both for diagnostic imaging and for therapy. For diagnostics, short pulses of ultrasound are passed through the patient's body. An echo reflected from a structure of interest is recorded, and the distance to the structure can be determined from the time delay for the echo's return. With sound of low intensity, this technique is non-invasive and relatively harmless. Again, it's non-invasive and relatively harmless. Much of what we know today to be ultrasound was often discovered in World War II with the advent of the sonar, where the American battleships would be able to detect enemy submarines through sonar. And the way sonar works is that it sends out pulses of sound, and they're reflected. Those pulses of sound are reflected off the submarine, and then based on the sound of the speed of sound in water, etc., and the what the sub is made of, and the density of the water, etc., they can determine if the sub is going towards them, away from them, what size the sub is. They can oftentimes tell very specific things about the sub in terms of its engine noises, etc. Anyway, to continue, it is used to examine fetuses, tumors, aneurysms. An aneurysm is if you ever saw a hose, like a garden hose, which has like a bubble in it, where it's an imperfection in the wall of the hose that could rupture. Same thing is true in our circulatory system. We can have an artery which has a weakened wall, and that's called an aneurysm. To reveal detail, the wavelength of the reflected ultrasound must be small compared to the size of the object reflecting the wave. The speed of ultrasound in human tissue is about 1,500 meters per second, nearly the same as the speed of sound in water. Now remember, the speed of sound in air is approximately 330 meters per second, and that's STP, and NTP, or normal temperature and pressure, would be 340. That's generally what we take it at. It could be 344, 343.5. This is a gallbladder. Ultrasound can also be used to determine problems with really anything in the human body that, instead of cutting someone open nowadays and doing what they would call exploratory surgery, they can do a variety of ultrasound experiments on a person's body to determine problems that, diagnose the problems. Ultrasounds are produced by a transducer. A transducer is a device that takes power from one source, converts the energy into another form, and delivers the power to another target. In this case, the transducer acts like a loudspeaker and a microphone. The transducer converts electrical signals to ultrasound waves, and picks up the reflected waves, converting them back into electrical signals. The electrical signals are returned from the transducer, go into the computer, and those converted waves are used to form pictures on a television screen. And you saw several pictures, several slides where you had images on a television screen. Those are actual pictures. Oftentimes the computer will enhance an image that the raw data might not really look like much, but the computer can enhance those and render a kind of a 3D representation of what might be in the body. Here are 4 different types of tissue in the human body. Notice that the tissue in the body, very similar to water, fat and body tissue, soft tissues, 1,500, between 14 and 1,500 meters per second. Notice bone, which is more solid, 4,100 Not as much as steel, but still bone was quite significant. This next one, there's two problems, A and B, similar to practice problems 1 through 6. It says, what is the wavelength of ultrasound with a frequency of 2.4 megahertz used in echocardiography to map the beating human heart? It also can tell you whether or not the heart is enlarged. Maybe the tissue that the heart is made of, the heart muscle, might be too thick. The valves in the heart, variety of things in the heart could be amiss. B is in the whole set of imaging techniques, frequencies in the range of 1 to 20 megahertz are used. What is the range of wavelengths corresponding to this range of frequencies? So what we'll see is we're going to do several problems here involving frequency, wavelength, and velocity. Remember, velocity equals the product of frequency and wavelength. Okay, so A, what is the wavelength of ultrasound with a frequency of 2.4 megahertz used in echocardiography to map the beating heart? Okay, well, we see that the velocity equals F lambda. Lambda equals V over F, and F equals V over lambda. And here we're going to calculate the wavelength. So it's 1500 meters per second divided by 2.4 times 10 to the 6th. Seconds to the negative 1, same thing as hertz. Seconds to the negative 1 is the same thing as hertz. And the answer is going to be 6.25 times 10 to the negative 4th meters. Okay, the next one, B. In the whole set of imaging techniques, frequencies in the range 1 to 20 megahertz are used. What is the range of wavelengths corresponding to this range of frequencies? Just notice that I'm using seconds to the negative 1 instead of megahertz. Anyway, so the wavelength, both wavelengths would be velocity over frequency. The first one is 1500 divided by 1 times 10 to the 6th, and the next one is 1500 divided by 20 times 10 to the 6th, which is 1 times 10 to the negative 3 and 7.5 times 10 to the negative 4, respectively. Now, if a train, of freight cars, well, I'll let you read this problem. This is an example problem that you should be very familiar with. Again, you'll see something very, very simple. We used to, back when we did mechanics, velocity was distance over time, but now we're going to do, the velocity is going to be wavelength times frequency, and that's up to you to make sure you know how to do that. Here's something very simple, reinforcement. So A, scenario A would be A would be constructive interference, and B would be destructive interference. So reinforcement is another way of saying constructive interference, and the cancellation, such as canceling headphones, would be B, destructive interference. Here are a couple of things, closed pipe, open pipe. I encourage you to read that section. I'm not going to spend a lot of time on it. Just make sure you can read it and that you've taken notes on it. Not going to be a big deal. What I want you to understand is that a musical instrument, for instance, a French horn, the player's lips vibrate, makes the air column resonate. Pressing the keys change the length of the air column. This contraption, this French horn, is a kind of a resonating chamber. Just by your lips vibrating is not going to really sound like much. But if I do it in this particular chamber, the the chamber helps to resonate and make it louder. Here I have a harp, same thing. The larger the string, the different the frequency. The shorter the string, different the frequency, of course. That's a harp. Strings of different lengths produce different pitches when plucked. Remember, any kind of instrument is really going to be a different way of resonating sound. There's a clarinet, the vibrating reed creates resonance in the air column. Again, it is to be understood that the clarinet itself, the structure of the clarinet, will act as a resonating chamber. We talked about a guitar. The box actually resonates, and you get that melodic acoustic sound in an acoustic guitar. The next shot is of a violin. The violinist uses a bow to force the strings to vibrate, placing his or her fingers at different positions on the strings changes the length of the strings. So when you change the length of the string, you're going to change the frequency. So when your fingers are high on the arm of the violin, what does that do? Okay. Here are sound levels. You have a jet engine, 140 decibels. You have a hearing threshold, which is at 0. Normal breathing, 10 decibels. And it goes up from there. Normal speech is 60 decibels. So these are decibels is a kind of a linear chart on sound levels. So if you're at a rock concert, you're getting up towards 110 decibels. So this gives you a pretty good evaluation of decibels, from being very quiet reading in your room to barely audible whisper. You hear various things, and when your hearing goes, you don't hear those fine frequencies anymore. Here is sound intensity. So you see, if you look at the X scale, look at the X-axis, where the distance is right there near 0, so you're very close to the sound source. You see that the sound intensity goes very high, and look what happens when you go away from the sound source. So the distance increases, you get this incredible drop-off. Here are some sound levels. I think I may have actually shown this one already. I think I did that. So you get 0 as the threshold, and that goes up to 140 decibels. And now what we're going to talk about a little bit is hearing, and it's very important to take care of your hearing. It's critical. Your teacher doesn't hear those finer frequencies, and oftentimes when I'm trying to listen to someone speak in class and someone is off to the side speaking, it's difficult to concentrate on hearing if I have a hard time hearing, when it's competing with the other noise in the classroom. Most of us try to protect our eyes from excessive sun, but few give the same care to our ears. Near loudspeakers during her first time at a concert, Allison was alarmed at the pain in her ears. Her friends meant to reassure her when they told her she'd get used to it. But what they didn't tell her was that after the fine-tuning of her ears was blasted, she wouldn't know the difference. So if you're getting used to sound, if you're getting used to a noise, that might not be a good thing. Pain in the ears is a good thing. It has a way of protecting you. Industrial noises is even more damaging to the ears than amplified music because of its sudden high energy peaks. Interesting. So, beware of industrial noise. Not to say that the high amplified sound at a rock concert wouldn't be bad for you. Here's the basic physiology, the basic structure of the ear. You have the outer ear, which is essentially the ear canal, and then you have the middle ear, which is the malleus, the incus, and the stapes, hammer, anvil, stirrups, and then you have the inner ear, which is the cochlea, and then you have the auditory nerve, which interprets material from the cochlea. Here is the path that the sound is taking. It is collected by the auricle, and then it passes across the tympanic membrane, which is your eardrum, and then it goes across the malleus, incus, and stapes, hammer, anvil, stirrup, and then it proceeds to go through the cochlea, and is then then it is interpreted by the auditory nerve. Here I have a fella who is using a jackhammer. Notice the noise canceling headphones he has. A little microphone on the side of the side there that hears the noise and tries to cancel it out, unless those are just simply earmuffs. Loud motorcycles, jackhammers, chainsaws, and power tools not only produce steady, high-volume sound, but also produce sporadic peaks of energy that can destroy tiny hair cells in the inner ear, in the cochlea. When these tiny sensory cells in the inner ear are destroyed, they can never be restored. Noise-induced hearing loss is insidious. Fortunately for music devotees, damage caused by energetic peaks is somewhat limited by an inadequate response of the electronic amplifiers and loudspeakers, which is probably, you're going to say to yourself, what the devil, what does that mean? Well, it's a good thing, actually. Fortunately for music devotees, damage caused by energetic peaks is somewhat limited by an inadequate response of electronic amplifiers and loudspeakers. The timing of this video is a little bit off, maybe a little too much time per slide, but let's proceed. We're almost through. And similarly, for live music, where most of the sound comes from amplifying equipment, if amplifying equipment were more responsive to sudden sound bursts, hearing loss at concerts would be more severe. The impact of hearing loss isn't fully apparent until compounded by age. Today's young people will be tomorrow's old people, probably the hardest of hearing ever. Start now to care for your ears and prevent further hearing loss. Not really trying to change your behavior here. This is physics class. But, it said something earlier where, we protect our eyes with sunglasses from the glare of sun, yet we don't ever think about, do we go to a concert and worry about, where we're sitting relative to the loudspeakers? Hey, just because an old person did it and can hear a little bit doesn't mean it's a good idea for a young person to, fall asleep with their headphones on. Although the headphones nowadays are, the quality of the sound is much better than it was years ago. Now, an application of sound would be a sonic toothbrush. Many of you may actually use it, where the bristles are vibrated in kind of like an ultrasound, just enormously quick vibrations. And what does that do? Well, that kind of drives the little bacteria in your mouth a little crazy, so that they really can't they can't really grow very well. They're disturbed, these little colonies that produce the plaque that leads to tooth decay. Noisy bugs, big bumblebees flap their wings at approximately 130 flaps per second and produce a sound of 130 hertz. A honeybee flaps its wings 225 flaps per second and produces a higher frequency sound of 225 hertz. The annoying high-pitched mosquito results from its wings flapping at 600 hertz. These sounds are produced by pressure variations in the air caused by vibrating wings. Now, if that bell jar is a vacuum, you can't hear it because sound does not travel through a vacuum. There's nothing to transport it, to propagate through. There's no way to get to the glass that could vibrate so that the person could hear. Just like the Starship Enterprise, you don't hear any noises in space. Sound, movies, space movies, Star Wars, etc., would be pretty boring if it was all silent. So you need the sound to kind of keep your attention, but just be advised that the sound doesn't travel in space. This is a kind of a peculiar little slide where you have two bells. Well, the bells have different sizes, maybe made of different masses. Each one has a unique natural frequency. When it rings, it will sound unique to its material. When any object composed of an elastic material is disturbed, it vibrates at its own special set of frequencies, which together form a special sound. We speak of an object's natural frequency, which is the frequency at which an object vibrates when it is disturbed. An object's natural frequency depends on the elasticity and shape of the object. Interestingly enough, most things from planets to atoms and almost everything else in between have a springiness to them and vibrate at one or more natural frequencies. A natural frequency is one at which minimum energy is required to produce forced vibrations. It is also the frequency that requires the least amount of energy to continue this vibration. Here I have a gentleman, when the string is plucked, the wash tub is set into forced vibration and serves as a sounding board of sorts. This is going to kind of get into resonating. What's actually making the metal of the drum play? Well, here I have 5 stages, A through E, and it says the first compression meets the fork and gives it a tiny momentum push. The fork bends, the fork returns to its initial position just at a time of rarefaction arrives. It keeps moving and overshoots in the opposite direction, and when it returns to the initial position, the next compression arrives to repeat the cycle. That's A through E. The pumping, the girl with pumping her legs, she is in rhythm with its natural frequency and produces larger amplitudes. This concept is resonance. The more she pumps her legs, she's pumping her legs at the same frequency as the swing, and you're producing larger amplitudes. I showed you a video when the Tacoma Narrows Bridge in Washington State was destroyed. You had In 1940, 4 months after being completed, the Tacoma Narrows Bridge in the state of Washington was destroyed by a 40-mile-per-hour wind. Soldiers will oftentimes, years ago, the old days, they would march over old wooden bridges and they would march out of step because they didn't want to destroy the bridge. Here is constructive and destructive. So the top one is constructive transverse. The next one is constructive longitudinal wave. The next one is destructive transverse. And the one below that is destructive longitudinal. So you need to know that for your test. You have to know what phase is. When you're out of phase, if you're 180 degrees out of phase, you're going to, one speaker is going to destroy the other. And that's what happened. The top one, they arrive in phase, so you get this amplified sound. Whereas if the speakers are arriving out of phase, you get this kind of like very quiet noise. It's quite the opposite. You get this reduction in volume as a result. What is happening with the person is rubbing the top of the glass, producing this very melodic sound, this resonance, because the energy that you're adding is the friction of your finger on the glass, and that's producing this very nice resonance, and that's the natural frequency. Here is these are two combs, and it's a wonderful example of what beats are. When you have two, you can see the teeth. The teeth on the blue comb are farther apart. The teeth on the brown comb are closer together. And when you put the two together, you get these compressions and these rarefactions. So where you get this thick, this thickness, that's going to be the compression, and the other will be the rarefaction. And here I have the production of beats. I have two separate frequencies, and I'm going to have a construction, and I'm going to have a destruction. And when I get the enhanced construction is going to be the actual beat. Now remember, if I have a 240 frequency and a 243, I'm going to have three beats. 240 hertz and 243 hertz. I'm going to have three beats. But remember, both the original tuning forks, you're going to hear both of them the same. Here's another one where I have three lines, and the first line was going to add with the second line, and you're going to get this constructive and destruction, and you're going to get this kind of beats with time. Now I have some problems to do. We have a standing wave. In the standing wave shown, what is the amplitude, what is the wavelength, and how many nodes are there? Okay. Well, let's see. It's 2.5 meters, and you'll see that there's going to be 1, 2, and a half. So there's going to be 2.5 wavelengths. So 2.5 meters. So each, if I have 2.5 meters, it's going to be 1 meter. If it's 2.5 wavelengths and it's 2.5 meters long, each wavelength is going to be a meter long. And then there's going to be 6 nodes because it crosses the x-axis at 6 places. And remember, the amplitude is going to be half the distance from the nodal line to the top to a crest. You see that the amplitude is 10 centimeters. The total distance, to amplitude would be 20 centimeters from the amplitude is not from crest to trough. The amplitude is from crest to nodal line. Again, you're going to have 1, 2.5 wavelengths, 2.5 meters total. So each cycle is going to be 1 meter. Okay, easy. All right. So I want you to do that one cycle. Do that once more, the wavelength of 1 meter, and then another wavelength of 1 meter, and then a half a meter. Okay? So now, let's look at the next slide, and it has to do with, a jet breaking the sound barrier. How do I know, what is the speed of the aircraft relative to sound? In other words, is it going to be Mach 1, Mach 2, Mach 3, Mach 4, etc.? And the way you find the answer is very simple. Take any round object, a ketchup bottle, whatever the case may be, and you just simply draw a circle. And then you simply measure, how many radii are there. And the amount of the number of radii, here there's 2 radii. And that means that it's, there's a lot of gobbledygook here. And there's far more gobbledygook than needs be. But the number of, there's 2 radii, therefore you're going to have Mach 2. So twice the speed of sound, as you can see, as can be seen by the angle of the shock wave. Each segment of the wave is a superposition of expanding spheres that were generated by the craft as it traveled along the dashed line. The center of any sample sphere, circle, as seen in 2 dimensions on the page, shows where the craft was when the sphere was first produced by comparing the distance the sound has traveled to the distance the craft has traveled in the same time. We have the speed of the craft compared to the speed of sound, and it's going to be 2 radii. Again, it's going to be 2 radii. So it's going to be 2 times the speed of sound. Okay, next one is a little bit more complicated. It says here that suppose at a concert, a singer's voice is radio broadcast all the way around the world before it reaches the radio you hold to your ear. This takes 1/8 of a second. If you're close, you hear her voice in the air before you hear it from the radio. But if you are far enough away, both signals will reach you at the same time. How many meters distance must you be for this to occur? All right, so what's going to be the time delay? So the time delay has got to be like 1/8 of a second. So time is 1/8 of a second. Now this is going to be velocity and distance and 1/8 of a second. So this is going to be using velocity equals distance over time, correct? Because you're given time and you want to find the distance. So we know that it's going to travel at 340 meters per second. That's the speed of sound. So how far will it travel in 1/8 of a second? Isn't that really what we're trying to find? So what we want to do is we say, well, if you sit 425 meters away from the singer, both the sound from the radio that is broadcast all the way around the world and that through the air will reach you in the same 1/8 second. Distance in the air equals speed of sound times time in the air. So 340 meters per second times 1/8 second is 400. Is going to be 42.5. My apologies. If you sit 42.5 meters away from the singer, both the sound from the radio that is broadcast all the way around the world and that through the air will reach you in the same 1/8 of a second, and that's going to be essentially 340 meters per second times 1/8 of a second. That's going to be 42.5 meters. So if you sit farther back, you'll hear the radio signal before you hear the sound signal. Rather basic problem. Looks a lot more complicated when we first read it than it really is. But if you pick things apart, you list some of the equations you have, you list what you have, you list what you're looking for, you should be able to do things very well. So good luck. Again, you can do notes on these on this video and turn it in for extra credit tomorrow. Have a great night, and get some sleep. Delayed opening, and have a good day, and goodbye.